All right, good afternoon, everybody. Looks like we're just almost to about 1 o'clock. Want to thank those of you that have signed on already for joining us. It's our first webinar for 2017, and we're really excited to have Ron Newman with Proof Technic here to talk to us about order measurements and condition monitoring. We're excited to have Proof Technic participate, and we're actually looking forward to them coming back down to our conferences in May. So we'll talk a little bit more about the dates for those as we get towards the end of today. But anyway, we're looking forward to that. Just some housekeeping before I turn things over to Ron. You all do have the ability to ask questions throughout today's webinar, and we encourage that. There's a little questions box in your little dashboard, so you can type those questions in throughout the session. I'll be monitoring those, and I'll get those tossed over to Ron as it's appropriate, or of course we'll have some time at the end for a Q&A session. So feel free to be interactive with us in that sense. I am also recording this webinar, so we will put it up on our website later today, hopefully, and so you can access it there. And if you've got colleagues that couldn't make it, or if you've got to pop off early, just know that will be made available. So we thank Ron and Proof Technic for allowing us to do that. It's always good to have these resources, and keep in mind on the webinar section of our site we've got all the other recorded sessions, so lots and lots of information up there for you all, and we're happy to be able to continue to provide those. So if, just also keep in mind we are doing this live, so if we have any technical issues, sound goes out, or any disruptions, we'll be sure to try and get it resolved as quickly as we can, but just bear with us. You just never know what technology is going to do to us. But with that, let me turn the screen over here to Ron. There'll be just a quick little pause while that happens, and Ron, will let you take it away.
Thanks very much, Maureen. Yes, let me just get this up and running here, and Maureen, maybe you just confirm that you are seeing my screen.
Yep, looks great.
Okay, so starting off again, just a welcome for my part to all the participants who are attending today's session. I was going to say this morning, but of course it could be afternoon, or it may even be evening for some of our participants. But this is the first in a series of UE seminars for 2017, order measurements in condition monitoring, order normalizing, order tracking, and order analysis. And while these are very distinctly different measurement techniques, unfortunately, they're often considered synonymous. So one of the objectives, and I hope takeaways for the participants, is to begin to see the differences between these three methodologies, that is, order normalizing, order tracking, and order analysis. There is some overlap of functionality, but in general they're employed for different reasons. So once again, good day. My name is indeed Ron Newman. I am a Proof Technique Sales and Support employee. I have 35 years experience in signal analysis, data acquisition, and specifically in condition monitoring. And right now you can't see me, but I'm pointing with my forefinger to my head, and I usually say I would have to have Teflon up here for something not to have stuck after 35 years. So, and once again, a big thank you to UE for hosting these educational and informative webinars. And as Maureen stated, the presentation is being recorded and will be available, I believe, on both our websites, the UE website and the Proof Technique website. So, starting with machinery vibration, machines contain rotating and reciprocating movements. That is to compress, to blow, to pump, transport, otherwise lift, drag, or perform some type of work. If there is no rotation or reciprocating action, then there is no work. And this rotation and reciprocating action will generate vibration. Now, under normal circumstances, this vibration is within sort of acceptable standards. But indeed, the vibration is transmitted to the stator portion of the machine, that is the stationary part of the machine, the base, the piping, the fan shrouds, the belts, the pedestals, and so forth. And as we know, when that machine vibration happens to coincide with a structural natural frequency, either the base, a fan shroud, the belts, piping in a pumping system, when we have a coincident vibration, then of course a condition of resonance exists, and that will amplify the vibration. So this is one of the factors that we have to be mindful of, particularly nowadays with VFDs, variable frequency drives. It seems that machines operate over a wide range of RPMs, so it's becoming increasingly common for resonance conditions to raise their ugly head, so to speak. And of course that will eventually lead to failure in the machine, either in a catastrophic sense, or a failure of a component, or a failure of the machine to perform the work that it's intended to. Machinery vibration, there are other contributing factors to that. The basic design of the machine is a factor. Any of the manufacturing tolerances and methods used to manufacture and produce the piece of equipment, the quality control processes or lack thereof that the manufacturer has implemented, installation and commissioning procedures, all of these are factors which will impact machinery vibration and performance. But to a greater extent, the practice of poor maintenance coupled with operating the machine beyond its peak performance envelope, and what I mean by that is running the machine pedal to the metal to produce the maximum production, making whatever widgets, running the machine in excess of its design capacity. All of these factors contribute to increased vibration, accelerating wear, and once again leading to failure. And our objective as vibration analysts is to avert that, is to at least be aware of problems developing and adjust our maintenance procedures accordingly. And one of the ways we do that is through vibration analysis. And so a key factor in the successful measurement and analysis, and I might add diagnosis of machinery vibration, is an accurate identification and or measurement of the RPM. And when we correlate the vibration data with RPM, in other words, we plot them together in some manner, this usually results in something that is loosely defined as order measurements. And what we're talking about today is order normalizing, order tracking, and order analysis. Now, I know that many of you attending the webinar are quite familiar with these terms. In fact, I'm sure many of you have already used some of these methodologies in the past. Certainly, order normalizing is one of the most common order measurement techniques. So let's have a quick look at order normalizing. It is something that is well known, but it's worth revisiting order normalizing to just reacquaint ourselves with the procedures we use to normalize frequency spectra. And of course, there isn't any advanced signal processing. There isn't any high-tech algorithms required to create an order normalized spectrum. It only requires that we have an accurate determination of RPM. And this is one of the things that we want to illustrate in a couple of slides here. But having identified the RPM, the x-axis, that is the frequency axis, is then labeled in units of RPM and correspondingly labeled 1x, 2x, 3x, x being the RPM. And so rather than displaying the frequency axis as hertz, that is cycles per second, or CPM, cycles per minute, it's labeled in orders. So it's a well-known technique and one worth, once again, revisiting. You know, there's several, or at least a couple of different options used to implement order normalized spectra. You can do it on site, typically in a state-of-the-art data collector, and or it can be done as simply a post-processing function in the host software. The principal applications we want to look at, we want to just again review some of the benefits to the vibration analysts. And as we are about to make critical decisions based on our diagnosis of these normalized spectral data, then it becomes equally critical that we measure the RPM accurately. And typically there's maybe a half a dozen or fewer techniques for determining RPM. And I've listed them here, as you can see in this slide. And beginning with, let's say, from the highest precision down to, let's say, the lowest precision, number one would be a measurement. And in today's modern world of data collectors, many of the data collectors have built-in strobe lights or methods of determining RPM accurately right on site. And that's always going to be perhaps the very best method. So we measure on site. The second method would be deriving the RPM from the spectrum. And of course, it's usually the fundamental, the rotational speed is usually the first peak in the spectrum. Now, I have to qualify that because, of course, with belt-driven equipment, often the load, the driven shaft, is running at a slower speed than the motor RPM. It's a ratio of the shift sizes, etc. So, but very often we have a reasonably good idea of where that 1x peak should be, and we can identify it in the vibration spectrum. The third, less accurate and not least, but one of the other methods is to derive that RPM from the motor nameplate. But once again, if it's a VFD, we'd have no idea of what RPM it may be running at. The fourth method, of course, when you built your database of machines and measurement points and measurement tasks, you probably identified the speed or speeds that the machine runs at. So that information would be available in the host data collector software. And lastly, of course, you can always gather it from the computerized maintenance management system, the CMMS data. So of all of these, probably the most reliable will be the first two. That is an on-site measurement and or deriving it from the spectrum. Both of these techniques will account for load, will account for VFD settings, process demands, and so forth. So what I would like to do now is just migrate over. I'm going to leave the presentation here just momentarily, and what I want to just illustrate an example of order normalizing in the field. So what I will do is I will just call up a file that has been recorded, and so we look at this file and we can see some pattern, and of course, looking at the Y scaling here, you can see that, well, you know, would I spend any time trying to analyze this particular machine? And the answer would be no, of course not, because the vibration is minimal, but it does give me some orders that I would like to show you. So so we can put the cursor, that's that little red dot there, on what we believe to be the fundamental, and then we can go and select a harmonic cursor, and select the harmonic cursor. And we see the harmonic cursor where I thought that this would surely be the second harmonic. With the harmonic cursor, it is not there. The harmonic cursor is down here. The third harmonic has a little X on it. The fourth harmonic is barely visible. So now I'm not 100% confident that this measurement at the main cursor is in fact the fundamental. So what I would want to do is I would want to come back to that main cursor once again, and now I have a technique. And this is, again, something that is available in most data collectors of identifying the peak more accurately. Now, we all know that lines of resolution and Fmax, etc., all of those things determine how accurately you're able to separate closely spaced frequencies or identify a specific frequency. But in the whole process of FFT analysis, we use something known as a window. We won't get into that this morning or this afternoon. It's another topic for another day. But the windowing creates something less than an exactly desirable result. So what we have is a routine, a small program that allows us to actually find the peak. And so you'll see right here that it's shown as 59.75. And at the bottom of the display here, you can see that that's approximately 3,589 RPM. So if I click on Find the Peak, you'll see that, well, it performs this calculation and identifies this peak more accurately as 59.88 hertz, i.e. closer to 3,589 RPM. So now when I go to the cursor function and I once again select the harmonic cursor, now we can see that we have this 2x identified, we have the 3x identified, 4x, and so forth. And furthermore, we could also go to and scale the x-axis. We can scale the x-axis in orders, and that would be done quite easily here, just by selecting orders, and now we have the x-axis labeled in order. So we can see that there's some degree of uncertainty even with the main cursor in identifying the fundamental. So you need to make sure that we derive that RPM accurately, because once again, critical decisions are going to be made based on how we interpret the spectra. So that's a way of determining the fundamental RPM. What about the load? Well, if the load is direct coupled, then the motor RPM is equal to the load RPM, if it's a direct coupled pump, etc., and so forth. But if it's belt driven or gear driven, then there's a quick little formula that we need to implement in order to derive the RPM of the load. And basically for belt driven equipment, it's reasonably straightforward. It's simply the motor RPM here multiplied by the ratio of the sheave diameters. So we take the input sheave diameter divided by the output sheave diameter and multiply that by the motor RPM, and that gives us exactly the load RPM. But this ratio right here, that is the input sheave diameter to the output sheave diameter, in my example is 0.75. So the load components in the spectrum will be at multiples of 0.75x. With the gearbox, it's similar. Again, now it's simply the ratio of the teeth, or if you know the ratio of the gearbox, of course, that would be useful. But if you know the number of teeth on the input pinion divided by the number of teeth on the output gear, this is for a single reduction gearbox, then that gives us the load RPM, but more importantly, this ratio gives us the factor of x that the load is running at. And this is important because this is going to allow us to identify things that are related to different RPMs. And you know, these are things that will hopefully help us. And just again, kind of reviewing some of the benefits of order normalizing spectra. Number one, and this is taken from some of the Mobius material, it helps us identify these three distinct regions within the spectrum. And this is something that I always try to encourage some of our users to use, and that is the ability to identify synchronous regions of the spectrum. And by synchronous, we mean that these are whole number multiples of RPM, so 1x, 2x, 3x, 4x, 5x, and so forth. We can see those right away. Then it also helps us identify non-synchronous components in the vibration spectrum. And And non-synchronous components could be related to the other shaft RPMs, like in the previous example of belt-driven or gear-driven equipment. Those shaft multiples would be non-synchronous. But very often non-synchronous components are often related to bearing frequencies, bearing vibration. And of course the third region would be subsynchronous. So once again, if we go back to our spectrum here, we have mostly synchronous components in this little spectrum. So we have a 1x, we have a 2x component here, a 3x, and a 4x, and yet here's a small little component that's not 3 and not 4x. It looks like it might be about 3.4. Now, this looks very suspicious. It may be a bearing frequency. And then we have some subsynchronous vibration here as well. So again, once again, breaking the spectrum, complex spectra, out into these regions really helps you identify the important points. It allows you to look at a clear indication of harmonic families, that is the family of 1x harmonics, and any additional families of harmonics. And generally speaking, harmonics are never a good sign. They're never something that you are encouraged to see. Whenever we see multiple harmonics, it's usually severe misalignment, some type of looseness, severe bearing problems, and so forth. So harmonics are very seldom a good sign in the world of vibration analysis. So let's have a look at a typical spectrum. So if we look at this, if I asked any of you to tell me what do you think about the spectrum, first of all, you might look at the Y scaling and say, well, this is a no-brainer. It's a small amplitude anyway, so we've got bigger fish to fry. But for the exercise, we'd have very little to say about this spectrum without any sort of information about the fundamental. Now, most often the analyst has an idea of where that fundamental is, and the process of order normalizing this spectrum would proceed as follows. So we might identify this peak, the first peak, as the fundamental, because in this case this is a belt-driven blower and this is the RPM of the blower. So first off, we would want to identify the fundamental and all of its harmonics, and we put a marker there. And so we've got the family of 1x components identified, and we have the x-axis now order normalized. So now we can see that we have some things that are not integer multiples of the 1x. And again, we might want to look at this peak right here as the driven shaft, mark it, and then all of its harmonics. So once again, we mark that peak right here, and then all of its harmonics. And now we're beginning to get a complete picture of this machine vibration. So all of the green little deltas are multiples of the load RPM. And are there any other peaks that have not been identified? Apart from these smaller ones down here, we have a couple of significant peaks that are yet to be identified. And of course, then it would be up to the analyst to dig a little deeper and see, are these related to this machine? Is the vibration being transferred from another machine through a common base? Or is it perhaps the onset of a bearing problem or harmonics of belt frequency? So this is the technique of order normalizing spectral data, and it's, I think, very worthwhile, something that should be encouraged for day-to-day monitoring of machinery vibration. Okay, well, that brings us to the subject of order tracking. And so with order tracking, we're going to leave the application of monitoring and trending data to diagnosing data. And order tracking is most commonly used to investigate resonances, to investigate critical speeds, or generally speaking, what is the rotor doing as a function of RPM. And so there are a couple of different ways that we can process order tracking information. So we want to look at those and discuss them a little bit. So the first method, of course, first of all, it requires that we have some type of a trigger signal, a tachometer signal. And so one of the first methods of order tracking is 1x tracking, tracking the fundamental as a function of RPM. And the second method is tracking the full spectra as a function of RPM. So if you see the background on this slide, we have amplitude along the y-axis, frequency along the x-axis, and it's not labeled, but that would be RPM along the z-axis going into the slide. So one of two ways to implement order tracking. Again, a common technique uses a probe, that is some type of a laser tachometer probe or perhaps a proximity probe, looking at a keyway to give you a once per revolution event. This signal is then used to track the amplitude of the vibration at the 1x. And because the tach signal is by definition synchronized with the 1x vibration, we also derive, in addition to the amplitude, we derive phase data. So as we track the 1x RPM from high speed down to slow roll, or from startup up to operating speed, we derive the amplitude of that 1x component, and we also derive the phase measurement. And when we plot these three parameters together using xy coordinates, this is typically known as a Bode plot. That is, in the illustration here, I have amplitude, and this is a measurement that I made a year or two ago. Basically, the machine was running up 3,000, 3,500 RPM, and I started the measurement around about 3,000 RPM. I've got that cut off here now, but I started the measurement about around 3,000 RPM, and we tracked the 1x vibration down through all the way down to slow roll. But when it got to around 700 RPM, there was a peak, and then it dropped off quickly through to slow roll. Again, that's amplitude versus RPM. Now we have phase versus RPM, and we can see the phase is fairly steady until I start approaching this peak. And as we approach that peak, the phase shifts roughly, you can see here, from 300, around 300 degrees to 200 degrees. So about a 90-degree shift at the peak, and then as the vibration amplitude drops down through to slow roll, the phase again shifts another 90 degrees down to the slow roll condition. So this is kind of a classic example of a slight resonance, and it's confirmed by the phase measurement. If we had just plotted amplitude versus running speed, this is not a 100% confident indication of a resonance. When we plot the phase, we can see how the phase changes 90 at the peak and a further 90 degrees as it goes through the resonance. Now, incidentally, this same data that we call a Bode plot, when it's plotted using XY coordinates, when it's plotted as a polar diagram in polar coordinates, it's known as a Nyquist plot. And once again, it's exactly the same data. There isn't any additional information that the analyst derives from the Nyquist plot that wasn't already there in the Bode plot. So the amplitude and phase are plotted as vectors. So from high speed down through slow roll, the amplitude is increasing till it peaks around 713 RPM. We can see that there's the classic 90-degree shift there, and then the amplitude begins to diminish as we carry on down through to slow roll. And again, overall, through the resonance, we see the green arrows indicate a total 180-degree phase shift. But again, it's the same information. Some analysts prefer to look at the Nyquist plot, others prefer the Bode plot. Myself, I prefer the Bode plot, but it's just a matter of personal preference. So the second order tracking technique is derived from a run-up or coast-down. And once again, the tachometer signal is used, but this time it's used solely to determine the interval at which we collect spectral data. So, simple setup then, we're collecting frequency spectra at well-defined intervals of RPM, starting maybe at 3,000 RPM, and then with the tachometer, we define a shift of 100 RPM as the trigger point to collect another spectra. So at 3,000 it collects a spectra, then at 2,900 it collects a spectra, at 2,800 it collects a spectra, and so forth all the way through to slow roll. And the data, as we see illustrated here, is plotted as the classic waterfall plot. Again, amplitude on the y-axis, frequency on the x-axis, and RPM on the z-axis here, not labeled, but this would be RPM. So, lovely techniques. Seems simple enough to set it up, but there is a note of precaution that needs to be identified here. And there are two very important Fft setup parameters that need to be balanced against the rate of acceleration if it's a run-up test, or deceleration if it's a coast-down test. Okay? And those two parameters are lines of resolution and Fmax. And we know that lines of resolution divided by Fmax give us a record length. That is, how much time does the analyzer have to gather, how much vibration data does it actually have to gather to satisfy the lines of resolution, or in other words, the delta F, the line spacing. So if we look at an example here, if we take lines of resolution of 1600, an Fmax of 400, and a record length of 4 seconds, and again, that's simply derived by dividing lines of resolution by Fmax, so the record length is going to be 4 seconds. That means it's going to take 4 seconds for every spectrum to be acquired. That basically gives us a delta F, or line spacing, of 0.25 hertz, or 15 cycles per minute. Now, what happens if the slew rate, that is the rate at which the rotor accelerates or decelerates, and typically these run-up coast-down measurements are made as a coast-down measurement, because typically machines start up much more quickly than they coast down. So in this case, you can see that this is the waveform, and it coasts down rather steadily and over a well-defined period of time. Now, if the slew rate is like 20 to 40 RPM per second, that means in every second goes by, the RPM changes by as much as 40 RPM, we can see that in 4 seconds, that RPM might change 160 RPM. Well, with 15 CPM resolution, that spectrum is not going to be very discrete. It's going to result in a smearing. A better result would be achieved choosing a different lines of resolution and or a different Fmax, or perhaps changing both of them. So once again, the machine RPM could vary by as much as 160 RPM in just one analyzer record length. And so that's equivalent to about 10 spectral lines. Yeah? And that's going to create smearing, and something that's undesirable. So the bottom line with respect to order tracking, specifically when we're plotting frequency spectra as a function of RPM, is that high resolution is not desirable. If you have a setup that defines a very high resolution, and your machine coasts down very rapidly, changes speed quite quickly, even in a sort of nominal manner. I mean, 10 to 20 RPM change per second is not uncommon. It's going to result in a smearing and a less than desirable result for your waterfall plot. So keep that in mind, And you know, a better measurement would be if we had lines of resolution of 400 and Fmax of 800, and once again, lines of resolution 400 divided by Fmax of 800 gives me a time record of 0.5 seconds. Okay? So this is going to minimize the effect of smearing. And once again, the bottom line with plotting and collecting frequency spectra as a function of RPM is that we're not really looking for high resolution, because what we're trying to look at is just the behavior of the machine. We're trying to look at resonances. If we were in a classroom environment, I might ask you the question of how would resonances appear on this waterfall plot? Well, what they would typically appear as is straight lines. They would appear as straight lines, whereas the harmonic data would appear as 1x, 2x, 3x fanning out from the origin. And as each one of the harmonics, starting with the highest harmonic, as it coasts down and goes through an area of resonance, it excites it. And then the first, the second, the third, and the fourth all excited. So that's typically the plotting technique that we use for frequency spectra as a function of RPM. Another way of plotting the data, I don't know whether all of you have seen this type of plot. It's called a contour plot. It's a little bit like a Campbell diagram. So it's kind of like looking at the waterfall plot from overhead, looking down on it. So on the y-axis, we have RPM. On the x-axis, we have frequency. And the amplitude in the contour plot is expressed as a color intensity. So the hotter the color, the higher the amplitude. The cooler the color, the lower the amplitude. And once again, we can see how the orders fan out from the origin. And if there were distinct resonant areas, these would appear as vertical lines in the contour plot. The Campbell diagram, again, looks similar, except that with the amplitude being represented as circles, and the diameter of the circle giving an indication of the amplitude. The bigger the diameter of the circle, the larger the amplitude. So that's one way of looking at the data when we do frequency spectra versus RPM. And from this basic data, we can derive the 1x amplitude. So from the waterfall plot, as we've seen here, we can simply derive the amplitude of the 1x as that profile of the 1x from high speed down to slow roll, and then plot that as a two-dimensional plot, again looking at amplitude versus running speed, RPM. Once again here, and this is another example again where the amplitude of the 1x component, or for that matter any harmonic, so if we wanted to see how the 2x harmonic behaved as a function of RPM, and the way we do that, there is a type of cursor that's available in some software called a slice cursor. And what that does is take a slice in the waterfall plot and plot that versus RPM. And again, it can either be the 1x component, or it might be any other harmonic if we wanted to see how the 2x component behaved or the 3x component behaved. So order tracking, used for diagnostic purposes primarily, investigating rotor behavior, investigating resonances, and critical speeds, and so forth. So now we're going to come back to the subject of order analysis, or at least not come back to it, but we're going to come back to the application of using a measurement technique that is primarily focused around the task of monitoring and trending. Occasionally, order analysis is used for diagnostic purposes as well. And we'll look at where it's very, very useful, where it would be preferred over order tracking. But order tracking is a simple setup. All we have to be mindful of is that lines of resolution and Fmax, and make sure that we have something that result doesn't give rise to smearing. So it's a fairly straightforward, easy to implement technique. Order analysis, on the other hand, is a little more sophisticated, but it gives us a better result. And for some types of machines, it's really the only solution for machines with varying RPM. And so if we look at the objective for order analysis, it's to collect data for comparison purposes from 1 month to the next month. That is, if you are using offline route-based data collection, that might be in 4 to 6 week intervals. Or if you have online monitoring of machines that have varying RPMs, that interval between measurements might be as 4 to 6 minutes. So, so again, for monitoring purposes, for trending purposes, and also for diagnostics. Let's look at a first solution to this issue of machines with varying RPM. And the first solution has nothing to do with order analysis, but it is a solution for machines with varying RPM. And it's something that we refer to as identifying machine states. Okay? And even though now, if we look at this plot here, this is an RPM profile, so RPM versus time, and we can see that in some periods of time the RPM is continuously varying, but there are short periods when the RPM is reasonably steady state. And so if we can define that RPM as a particular machine state, then we're able to collect data with the hope of reasonably good repeatability. Okay, and that's the key there. So that would be a solution for machines with varying RPM, but machines that do have short periods where the vibration is reasonably a steady state. On the other hand, for those machines where the RPM is continuously varying, and typical machines that exhibit this type of behavior are found in the mining industry. Shovels, drag lines, these are machines that are continually working, continually creating vibration through different RPMs, but the RPM never has a steady state period, or at least not a period that is long enough where you could define a machine state and collect data. And a year or so ago, I gave a paper on monitoring machines in the mining industry, and one of the solutions, apart from order analysis, one of the solutions that we recommended was we simply run the machine during a PM period and run it steady state. Now, under no load, this is probably not going to be representative of the vibration that we would have when the machine is operating. In any event, it's an attempt to get some repeatability to the measurement. So that's not something that's uncommon. I've heard of many consultants that do that. They simply come in on a day when there's a PM schedule for the shovel or the drag line, and they simply run the machines at steady state RPMs and collect the data. But no, when we want to collect the data and be fully under load, then we have to compensate for this varying RPM. And the way to do that is with order analysis. It gives us reasonably repeatable results. And so, looking at order analysis, how do we define it? And I don't know about the participants. Myself, I refer to Wikipedia probably maybe as much as half a dozen times a week. I think it's a wonderful source of information. It's user-enabled, so we have to be careful about what we're reading, but in general, it's pretty good data that we can find on Wikipedia. And this is a quote directly from the page that's listed at the bottom there. If you're interested in clicking on that or getting that link, that will be available in the presentation on both the UE website and the Proof Technique website. So just reading from their definition, it says, in rotor dynamics, order analysis is a family of signal processing tools aimed at transforming a measured signal from the time domain to the angle or order domain. So our discussion today has to do with order domain. What could they possibly mean by angle domain? This is a relatively new signal processing technique that is gaining widespread popularity, particularly in the automotive industry, where we want to collect data specific to an angle of rotation. And so if you think about the angle of rotation of the crankshaft in a reciprocating engine, that at a certain angle of rotation, we know that there are certain events happening in that machine. The cam is in a certain position, valves are opening, closing in a certain sequence. And so collecting data as a function of angle of rotation holds a lot of promise for certain industries. But our discussion today has to do with transforming a measured signal from the time domain to the order domain. So these techniques are applied to asynchronously sampled signals, that is, signals that are sampled with a constant sample rate, such as we have in an FFT. That constant sample rate is a function of Fmax, and it happens to be 2.56. That's that magical weird number that we use to define a sample rate. But in any event, so these techniques are applied to asynchronously sampled signals in order to obtain the same signal sampled with a constant angle or order increments of a reference shaft. And what it results in is an order-based spectrum. And this is extremely useful in our measurements. Now, the setup for an order-based or an order analysis basically is configured to derive a sample rate as a function of RPM. So if we look at the top signal here, the waveform, we're going from slow speed, long period here, up to high speed, where it's a shorter period. So we're going from slow roll up to some operating speed. Now, with a constant sampling rate, we can see that at the low frequencies, we have X number of samples per period, but as we increase in RPM, we get fewer and fewer samples for that signal. And combined with other factors, this will lead to smearing. And just a rough illustration here of what that smearing looks like, and we saw it earlier in the example of order tracking. So smearing is something that really jeopardizes the whole business of frequency analysis. So what we do is we then configure a tachometer signal and derive the sampling frequency as a multiple of that tachometer signal. In this illustration, we're looking at 8, and that's the number of orders that the user wants to measure. So if he says, I want to be able to see 8 orders of the fundamental, then the sampling frequency is derived as 8 times the fundamental. And as we can see here now, we have a constant number of samples in the waveform. And the waveform now is in revolutions, not in time. This is a key point here. So when we go to order analysis, we move from the signal being sampled in time to the signal being sampled in revolutions. Okay? And what that ultimately gives us is a spectrum, an order normalized spectrum. And it means that irrespective of the RPM, the 1x will always appear as a line at the 1x position, irrespective of the RPM. So how do we set this up? It's not particularly difficult. The basic FFT parameters are things like Fmax, lines of resolution, windowing, etc. And where we go to order analysis is where we substitute the order max for Fmax. Yeah. So in other words, in this illustration here, the user has suggested or looked at it and said he wants to see 80 orders and with a line spacing of 1600. Now, these relationships, when we interpose order max for Fmax, the parameters, the ensuing parameters are calculated in exactly the same way. So, for example, if we have this lines of resolution set for 1600 and the maximum number of orders set for 80, and again, this is the parameter that's regarded as the Fmax in our FFT signal processing technique, when we take 80 and divide it by 1600, we came up with, if we take 1600 lines of resolution divided by order max, that gives us T, the record length. And in our example, 1600 divided by 80 gives me 20 revolutions. Once again, remember that the record length is going to be in revolutions here, not in time. Yeah. So, and also we can further say that because we have 20 revolutions, that is T, right? And we know that the reciprocal of T, 1 over T, gives me the line spacing. Once again, in order analysis, it's not referred to as line spacing as such. What we have, we come up with a parameter known as delta order. So 1 divided by 20 gives me a delta order of 0.05. In other words, I'm going to have 20 lines for every order in the spectrum. That gives me a good ability to separate out closely spaced orders. So, the sampling rate of an order analysis measurement is governed by the RPM, and of course the components, as I've mentioned, 1x, 2x, 3x, always appear in the same line in the order spectrum. A quick summary here. If we look at FFT-based order tracking, when we talk about time, we're talking about clock time in seconds. When we talk about frequency, that is, we're talking about how often. Again, we're talking about events per second, that is hertz, cycles per second or cycles per minute. On the other hand, when we're talking about RPM-based order analysis, the time is referenced to RPM. So the record length is in RPM, not revolutions, not in seconds. And the order spectrum, again, is how often per revolution, harmonics, orders of X. So this can be done in the field, as we've illustrated, with a basic setup there. More often than not, nowadays with online systems, it's derived as a post-processing function, typically. So the RPM data and signal are collected synchronously and through some very fancy algorithms, through a process of RPM profile interpolation and resampling, we then are able to create the order spectrum. So what does it do for us? Apart from avoiding things like smearing, the operator is going to get a very good picture of the equipment condition independent of RPM. So it enhances, well, let me say not truly independent, but we avoid the issue of smearing. So we can look at these components and trend the 1x over time quite easily, quite readily. It basically enhances that ability to trend, but also diagnose critical rotating machinery. So again, looking at the presentation of the data, in the upper left we have order spectra, and it's quite easy to see the 1x components. Even though the RPMs have varied considerably, we can look at the 1x and see how it's changing. We can apply some smoothing algorithms to get a very good trending picture. Whereas when we do try to do some trending or comparison of 1x peaks without order analysis. We have the issue of smearing. We have the issue that they aren't a straight line in the waterfall plot, etc. So order analysis really improves that. It's another tool that hopefully you will be able to consider. So order tracking versus order analysis, once again a similar sort of summary here. Order tracking without sampling, some of the advantages is it's a simple setup. It's pretty easy to set it all up. We can define a start RPM and a finish RPM. We can define the interval at which we're going to collect spectra from the tachometer signal. The only thing we have to be aware of is making sure we choose lines of resolution and Fmax accordingly. It helps us identify resonances, and it's relatively easily understood. Disadvantages, it can result in smearing. That's one of the biggest advantages. Disadvantages. With order analysis, there's no smearing. We have identification of higher harmonic orders, and it will accommodate a wider slew rate. That is, depending on how fast the machine changes RPM, either when it's accelerating or when it's decelerating. Disadvantages, of course, it requires more processing power and, most importantly, a very accurate tacho signal. So that's today's presentation on order measurements in condition monitoring. We've looked very briefly at these three techniques: order normalizing, order tracking, and order analysis. These are tools that we can use to better understand machinery vibration and hopefully somehow avoid failures in the machine. And it's my hope actually that the participants have been able to gather maybe one or two little bits of information, piqued your interest a little bit to perhaps act as a catalyst for you to go out and explore some of these techniques in your own plants. So once again, I want to thank the people at UE for hosting this. This is the reference material, or at least my sources for some of my reference material in the presentation today. We do have a little time here at the end. This will also be part of the slide presentation that has been recorded, so if you want to contact me by email or by phone, I'm more than happy to speak with you directly. And again, once again, a big thank you to UE Systems for hosting not only this seminar or webinar, but a whole series of them. And this is always good information for vibration analysts. So lastly, thanks again to all the participants. I hope you enjoyed this morning's or this afternoon's session. And I'll turn it over now to Maureen, if you're there.
Yep, I'm here. Awesome. Thank you. That was quite some good information, and yeah, I think glad we were able to record it so folks can go back and have another look. Already had a few people say, wow, this is really great, but I'm going to need to watch it again just to, as you said, pick up even more than just the one or two things they might have grasped this first time. So just maybe one or two questions real quick, and then we'll wrap up. If we don't get to your question just due to timing, we'll make sure that Ron gets it and he can hook up with you offline to help you out. Some of these probably make more sense for an offline discussion anyhow. So here's one that came in. They said, we have rolls that are being run between 70 and 150 RPM. Can we get a good reading using one single accelerometer as opposed to a triaxle?
Yeah, I believe you can. First of all, this actually, Maureen, this sets me off on a tangent, and I don't want to go there, but and this is a personal observation from myself. Number one, I'm not a great proponent of triaxial accelerometers. Horizontal, vertical, and axial at each and every measurement point seems to me to be a bit superfluous. But in any event, I think to answer your question more directly, for RPMs running between 70 to 150 RPM, one accelerometer correctly placed on the bearing, and I'm assuming that this gentleman or lady is in the paper industry. He's probably referring to felt rolls or dryer can rotational speeds, possibly. But yes, the answer would be one accelerometer. typically in the axis of least stiffness. For most machines, that would be horizontal, but it might be axial in the case of some of those issues peculiar to her industry.
All right, cool. And you put your email address up there so folks can obviously ask you for some more detail. Just a couple people had actually asked where they could maybe see more information like this. I know on our UE Systems site, in our training section where we have our archived webinars, we've done a handful of vibration webinars in the past, but certainly wouldn't have as many resources as I'd imagine your website would have. And you had flashed that up there. So it's just prooftechnic.com, right? Is the website. And
bksv.com is a wonderful resource as well. Before my time with Proof Technique, I was with Brule & Care for some 20 plus years. Wonderful company. They have, for probably in many cases, derived a lot of very useful information in terms of data acquisition and signal analysis. So I would refer them to that site as well for additional resources.
Yeah, and I know Mobius, you had put their website up there. You know, they launched last year a new conference that we participated in. I believe you guys were there too, the International Maintenance and Vibration Conference, and I know they're doing that again this year in several different locations. So if this is really of interest, that might be a conference worth taking a look at for sure.
Yeah, absolutely. Yeah.
So just want to run through before we let everybody go. And Ron, again, thank you so much. Really great, and really appreciate the support and the information. For those of you that are on here who were looking into vibration, but you're currently using our ultrasound as a technology, just want to remind you that we've got our online mechanical inspection and lubrication training course and our compressed air survey online course available. Really great. You kind of self-directed, you work your way through the modules. So if, again, you're looking for more information, especially on the mechanical side, if that's of interest, we've got those available. And for those where lubrication is a hot topic, we will be doing our Lubruary again next month. And it'll be the third year now that we're doing it. So the whole month, all of our webinars, we're going to do 3 of them. They're all going to be geared around lubrication and lubrication best practices and all that good stuff. So we're looking forward to that. We've always got a lot of good participation, so we know it's a hot topic. So we want to get that covered right at the beginning of the year. And we've got obviously all the presentations and things archived from the past, so you can check those out too to start getting a jump start on it. And we've mentioned a few times our website, a great resource. Ron mentioned, their website and other sources, but definitely take a look at our UltraProbe users group on LinkedIn. Follow us on Twitter. Just another great resources where we're trying to share as much information as we can, not just on ultrasound, but obviously the complementary technologies like vibration and infrared and so on. So hit us up there and save the dates. I mentioned that Ron and Proof Technic, they're going to be down at our conference, Ultrasound World and Reliable Asset World. They're co-located in beautiful Clearwater Beach, Florida. And actually, Florian, the North American CEO for Proof Technic, is actually the one who's going to be presenting. So we're looking forward to having him down there. And anyway, just great places to come and learn some more, network, and you can't beat Clearwater Beach, Florida. It's gorgeous. So we hope you guys will save the dates and check that out. And with that, I will leave our contact info up for just a little bit here. We'll get that recording up on our site as soon as we can. Shoot me an email if you want me to send you the direct link to that. And we'll let you guys go and have a great rest of the day. Ron, thanks again, and we'll look forward to seeing you guys back here in February.